Okay, welcome to this recorded lecture. So in this lecture, we're going to look at the theory behind simulated annealing. And in particular, we're going to show that the method is guaranteed to converge to the global minimum with probability 1 for any initial value, any initial guess, x0. So we start here with some preliminaries and some background knowledge. And if you're following in the type notes, we're looking now at section 17.2. So remember, in simulated annealing, we are literally simulating the quench of a system to absolute zero so that the system collapses into the minimum energy state, and this corresponds to the global minimum of a cost function. So we start with an initial temperature when we're simulating the quench, T0. And so T0 is meant to be a high temperature because we quench from a high temperature to absolute zero. So we start with this initial temperature T0, and correspondingly, we start with an initial state of the system, and this is analogous or equivalent to an initial guess for our minimizer, and we call that x0. We then generate a new guess, and in this context, we call it a proposal, and the proposal is to move the system into a new state x1. And in this algorithm, in this simulated annealing, where we're simulating the quench of the system to absolute zero, we accept the new guess. Um, well, with the following kind of scheme. If the new state or the new guess reduces the cost function or the energy, then we accept the proposal with probability 1. So just in symbols, the new energy is E1, and it's E, which depends on the new state. The original energy is E0, which depends on the initial state. So the change in the energy is E1 minus E0, final minus initial. So the probability that we accept the new guess and accept the proposal and go from x0 to x1, it's 1 if the energy is reduced. And here's the key thing about simulated annealing. If the proposal increases the energy, we accept it every now and then with this probability here. We generate a sequence of guesses or states like this, and this corresponds to the system. This corresponds to a system being cooled, as we'll see in a minute. So after a certain number of steps like this, we reduce the temperature to simulate the cooling to a new temperature T1. And we continue like this. So we sequentially generate new guesses or new proposals, new states for the system. We accept the proposals with a certain probability. And after stepping through a certain number of states like this, we lower the temperature again. And we need to lower the temperature in a systematic way, and this is called the annealing schedule. Now, crucially, this algorithm for stepping from one state to another, it satisfies a key property called detailed balance. So here, PT is the Boltzmann distribution. So PT times the transition probability, the probability to go from xk to xk plus 1, is equal to everything flipped around. It's equal to the transition probability, or sorry, it's equal to the Boltzmann probability evaluated at ek plus 1 times the transition probability to go from k plus 1 to k. So this combination of probabilities is the same after you flip around the k and the k plus 1. And this is called the detailed balance property. And this is a key property of the simulated annealing algorithm, and it actually guarantees that all parts of the phase space are sampled. So in other words, stepping through the states like this, generating proposals, and then accepting them with a certain probability, it guarantees that this process is ergodic. So all parts of the phase space are sampled. So this sounds fairly abstract, but the algorithm for implementing this simulation is relatively straightforward, and it's given in the type notes in section 17.3. Moving on to section 17.4, we discuss the annealing schedule. And the aim here is to justify this choice so that Tk the temperature in the kth cooling cycle is less than or equal to T0 over ln of k. So the aim of this section is to show that this is a good annealing schedule, and in doing this, we will show that simulated annealing converges to the global minimum with probability 1. So this is a nice calculation, quite theoretical, but very satisfactory at the end. So the strategy here is to start with an initial guess, x0, and we generate the new guess, so we generate a proposal, by drawing a vector or a state from the normal distribution. So that x1 will be normally distributed around a mean of x0 with standard deviation sigma k. And we take sigma k squared to be tk. In other references, you'll see sigma k squared equals twice tk. Both choices work. This particular choice is called Boltzmann annealing. So this is how we generate the proposal. We draw a proposal from the normal distribution centered at the previous state, x0, with a standard deviation of sigma k. So the probability that the new proposal can be found in a particular region R of phase space is then an integral. So this is the probability that the new proposal or the new state is in the region R. It's just the integral of the probability distribution function over the region. So standard probability theory. And here, because we're drawing our proposals from the normal distribution, P of x is the normal distribution, the normal probability distribution function. So it's the Gaussian e to the minus L to the norm of x minus x0 squared over 2 sigma k squared, and this normalization factor here, and this is an n. So this is a standard normal distribution centered at x0 with standard deviation sigma k. So as indicated previously here, we're looking at this annealing schedule, where in the kth cooling cycle, Tk is less than or equal to T0 over ln of k. So this is our simulation for the quench. After a certain number of steps where we accept or reject new proposals, so we move the system from one state to another. After a certain number of these steps, we reduce the temperature according to a formula like this. T0 is the initial temperature, and it's supposed to be sufficiently large. We'll specify what that means precisely in a minute. So now we want to show that if you follow this recipe, that the system will converge to the global minimum. The minimum energy state is reached. So the idea now is to look at the probability GK. And this is the probability that the new proposal is to be found in a small volume delta V in the phase space centered around the global min. So we denote this as region R centered at x star with volume delta V. So GK, by definition, is the probability that the new proposal is in this region R centered at x star, the global min, of volume delta V. And again, this is the integral of the probability distribution function over the region in question. And just specifying that the probability distribution is the normal distribution function. So GK is the integral over my region of the probability distribution function. And this is an exponential, and it's the L2 norm. So this is n copies of a Gaussian. So e to the minus x minus x0, 1 times the same thing n times. So this integral actually breaks down into a product of n separate integrals. And in the first integral, I'm integrating over dx1, and the contribution to the exponential is e to the minus x1 minus x 0, 1 squared. And the 0 is coming from the fact that this is the mean. So I'm drawing the proposal from a normal distribution centered at x0 and with a standard deviation sigma k. So this is just the mean. And there are n such exponentials. the last one is my variable xn minus x0 n squared, integrating with respect to xn. And the region of integration in question, I'm going from x star 1 minus delta x over 2 to x star 1 plus delta x over 2. So x star is the global min, and it's x star 1 all the way up to x star n. So all the way here up to x star n minus delta x over 2 to plus delta x over 2. So I've broken up my volume into a hypercube, and in each direction in Rn, the volume has a scale delta x. So delta x to the n is the volume of this small hypercube. So then in this way, GK can be approximated. So skipping ahead slightly for a second, in this approximation, I'm going to use the trapezoidal rule. So the integral of f of x dx from a minus delta x over 2 to a plus delta x over 2 is well approximated by f at a times delta x, a being the center of this small region of integration of interest. And this approximation is valid for smooth functions. So going back up and applying the trapezoidal rule to each of the integrals, I get my exponential e to the minus x star 1 minus x0 1, because here I'm evaluating at the center of the region of interest. Which is x star 1. And then minus x0 1, I subtracted off, that's the mean. The distribution is centered at the mean. Squared over 2 times the standard deviation squared times delta x, coming from the trapezoidal rule. And our normalization. And this is repeated n times, because there are n contributions to the integral. And I can then gather up again all of those exponentials into a single exponential involving the L2 norm squared of x star minus x0. And I've got the delta x to the n in front because I have n copies of delta x. And I recognize that as delta v. So summarizing, this is what we have so far. GK is delta v over 2 pi sigma k squared, which is just tk, times e to the minus the L2 norm of x star minus x0 squared over 2 sigma k squared, and sigma k squared is tk. So this is what we've done so far. And remember, this GK, it's the probability that the new proposal, starting with x0 and making a proposal x1, it's the probability that the new proposal is found in a region of space centered at the global minimum with a small volume delta v. So it's actually more useful to calculate the probability that the system will not enter this region. And particularly, we want to show that the probability of the system never entering this region, as you step through infinitely many different states, and as you cool the temperature according to the annealing schedule, you want to show the probability that the system will not enter this region goes to 0 as the number of cooling steps goes to infinity. So if the probability that the system is not in the region, if that goes to 0, then the probability that the system gets into the region is 1. So it suffices to show this. So this notation here is for the product. So this is the product because it's an and in probability. It's the probability that the system is not in the region after cooling step 1, and the probability that the system is not in the region after cooling step 2, and so on and so forth. So you want to show that this goes to 0. So it suffices to take logs on both sides and to show that the log of the product of the probabilities goes to minus infinity. Because so log of a small number goes to minus infinity, as the small number goes to 0. So taking logs on both sides, it suffices to show that the log of the product of the 1 minus gk's goes to minus infinity as the number of cooling steps goes to infinity. Now, I use the fact that the log of a product is the sum of the logs. So it suffices to show that the sum of the logs of 1 minus gk goes to minus infinity as k goes to infinity, as the number of cooling steps in the schedule goes to infinity. I can assume gk is small because it's proportional to delta v, which is the small volume in the phase space. And I can Taylor expand log of 1 minus gk as minus gk. So now it suffices to show that the sum of the gk's goes to plus infinity as k goes to infinity. So if I can show this, then it's equivalent to showing that the probability that the system enters the region R goes to 1. And again, this is equivalent to filling in for what gk is. This is equivalent to having to show that the sum over k of 2 pi tk to the n over 2 times e to the minus x star minus x0 squared over 2 tk, that this goes to infinity. And we're given the annealing schedule, that tk is less than or equal to t0 over ln of k. So filling in for tk, it suffices to show the sum over k of log k of n to the power of n over 2 times e to the minus, so filling in for tk, e to the minus ln k times x minus x0 squared over 2 t0, that this goes to infinity. If we can show this, we're done. We can reason back up the chain to show the probability of the system entering the region R goes to 1. So back to the meaning of t0 large. We want to choose t0 large such that this is less than or equal to 1. And then it suffices to show, referring back to this inequality, that the sum over k of log k to the n over 2 times e to the minus log k, x star minus x0 squared over 2 t0, which is now less than or equal to 1. So it suffices to look at this, because we have this bound, since this guy is less than or equal to 1. So this sum of k log k to the n over 2 e to the minus log k times the L to norm of x star minus x0 squared over 2 t0. This is greater than or equal to the sum over k of log k to the n over 2 e to the minus log k. So we want to show that this is a divergent series. And if this is the divergent series, we can reason back up the chain to show the probability of the system entering the region R goes to 1. And indeed, it suffices to look at the tail of the series. So we take k greater than some lower cutoff k0, and we look at the sum from k0 to infinity of log k to the n over 2, e to the minus log k, x star minus x0 squared over 2 t0. And since t0 is sufficiently large, this is greater than or equal to the sum over k, starting at k0, of log k to the n over 2 e to the minus log k. And e to the minus log k is 1 over k. Log k for k sufficiently large is greater than or equal to 1. So again, if I pick the tail of the series, so this will certainly be true. So this sum is greater than or equal to the sum from k equals 0 to infinity of 1 over k. And this is precisely the harmonic series which diverges. So reasoning back up the chain, the sum that I had, log k to the n over 2 e to the minus x star minus x0 squared over 2 tk, that's divergent. So this goes to infinity as k goes to infinity. And so again, reasoning back up the chain, the probability that the system stays away from the region R after repeated steps in the cooling schedule, that goes to 0 as K goes to infinity. And so the probability of staying away from the region goes to 0. And so the probability of reaching the region and therefore being within delta V of the global min goes to 1. And this completes the proof.